Hello, my name is Harrison Cassidy, and I made a system dynamics model here my senior year at Woodrow Wilson High School in Portland, and I currently just finished my second year at Oregon State University in chemical engineering. And the model that I did was a worker satisfaction model. So the goal was to model how the workforce of a company changes based on various factors. So the problem, as I said before, is how does the workforce of a company respond to changes? So in my model, I had several different factors, which are things that you can change, test, and whatnot to see how things change. So so some that I had were about the amount of work, so how much work is there to do. An employee safety net, which is basically a company policy that says how many more employees than we need do we want in case to respond to changes in demand. And a productivity slowdown, which is like a strike, not a full strike where everyone quits, but where workers specifically work less in order to protest, and also wage changes. So these were several things that I was able to change in my model to detect the responses, which are the number of employees, the amount of unaccomplished work. So if the employees aren't doing their job, work will build up. And so you can use that as a response. The satisfaction of your employees, and the productivity of your employees. So basically you can vary the factors to see how the responses change. And obviously you can sometimes test different factors that you can find in the model as well. So here's an example scenario that I ran. So it starts here at steady state, which is the same for all my tests, which means you start at a state where everything is in alignment. And then on the fourth week, I increased the amount of work 500 units for a duration of 4 weeks to see how the company responds. And so as you can see, when this amount of work comes in, the amount of work needed to do, which is the amount of backlog work, shoots up quickly, which has several different effects, such as the number of employees, which takes a little longer to get up there, along with the satisfaction of your employees, which dips when the workload increases so significantly quickly, but does increase once more employees get hired. And so, the question is, when you're building one of these, you want to find out how to minimize these drastic changes. You want things to remain as steady as possible. And so that's sort of the goal when you're modeling these, is to sort of see how this whole system responds to different changes in some of our factors. So in creating my model, I first had to choose the main things that I'm going to be modeling, which I chose employees, perceived satisfaction, and work. And each segment of my model, the fundamental basic of it is a delay. So I set up every part of the model as a delay because, especially in this type of model, no response is going to occur instantaneously. There's always going to be some sort of delay, whether it's this material delay between the amount of work coming in and the time it takes for it to get completed, or these information delays, such as when the amount of work increases quickly, how long does it take for you to hire new employees, and that kind of thing, and get them registered. And same thing with satisfaction, where say your workload increases, but it's going to take a while before people realize that they're being overworked and the satisfaction decreases. These things just don't happen instantaneously. Instantaneous change doesn't happen in the real world. Things always take time. So I started each segment as some form of delay, and then the next process in building the model was connecting each segment. So here's an example where I connected the work with the perceived satisfaction. So the goal here is to detect different ways where they can be connected, which ultimately creates different feedback loops. So for example, in the connection from satisfaction to work, or at least one of the main connections, the satisfaction increases the stress ratio, which causes people to be more stressed, altering the productivity, which ultimately affects work completion. So basically what you have to do is you have to go through each segment of the model and discover these different connecting factors and use them to link the models. And so once all of these are done, you can go through, and what's really interesting to do is to go through and see any loops that you can create. So here's one loop that was pulled from this model, and it's the main worker satisfaction loop. And so basically what happens is the amount of work increases, increasing the workload, which increases the expected wage of the people, because when people are working more, they expect more compensation. And since they're expecting more money, their satisfaction, but they're not getting it, because you're holding all other things constant, they're not getting it, so their satisfaction decreases, which increases the amount of stress, ultimately decreasing productivity, which decreases work completion, and finally decreasing the amount of work completed. So this is sort of the example where you change one thing, so you change the amount of work, and ultimately it comes around and causes that amount of work to keep continuously decreasing. And so it's important to analyze these different feedback loops, because that ultimately determines the behavior of the model. So, for example, if you have this form of feedback loop, this reinforcing feedback loop where you decrease the amount of work and the work keeps going down, you need to have some form of counteracting feedback loop to keep things in check. And so being able to discover and analyze these feedbacks is probably the number one most important tool to understanding at a fundamental level how your system works and how your model works. And so if you go back to this, you can easily see that loop here: stress ratio to productivity to work completion, which changes your work, changing your workload, which changes the amount of satisfaction, ultimately changing that. So there are many loops that can be discovered in these models, and it's important to understand them in order to further your understanding of this model. So next I'm going to show you my final model. You can see the work, employees, and satisfaction. There's also a wage section of this model that I haven't discussed, and the reason I did that is because it was sort of an afterthought that I had initially added, but I discovered that it would be too complicated to connect it. But it's in there if it were to be further expanded. So this is my full model. You can see how everything's connected if you take a closer look. It's pretty easy to read through. One fun thing to do with these models is to do tests to discover different policies you can implement to cause the changes to be better than if you had none. So here's one run that I did where I'm looking at the number of employees at a company. And this is the same scenario as you saw before with a 500 unit work increase for 4 weeks at week 4. And what I chose for my response was number of employees. And each line, this top line, is an employee safety net of 1, 1.02, 1.04, 1.06. So that means, what those numbers mean is this second one means that you take 2% more of your employees than you need to just remain at a steady state. And so what you can see from the simulation is that when you have no safety net, it jumps up significantly and then comes down here and starts oscillating a little bit. And when you have a really big safety net, it doesn't jump up nearly as much and it smoothly comes down. But the deal is, the more, with this one, even though this one's a little more stable, you have so many more employees for so much longer that it really economically doesn't make sense. So, for example, in this case, I recommend an employee safety net of 0.02 because if you look here, the variation in the oscillation is very low. It's fairly smooth, and you ultimately don't have too many more employees. So this is sort of an example of how these models can be built and used to analyze a complicated situation. And, you know, it'd be very difficult to come up with this kind of information from any other form of, numerical analysis with equations and whatnot. Whereas with Stella, it was very easy to create a model and discover this this pattern. And so the question is, what did I get from taking a system dynamics class? I would just say the number one thing I got from system dynamics is a new way of thinking. Being able to analyze and think about things in forms of feedback loops and how things are interconnected is probably one of the best things I could have ever taken from this class. Now when I look at systems such as, you see them all around you, I think of the environment, I think of that as a system, populations, it's everything. Once you learn how to analyze things with feedback loops and delays, you realize that the world is nothing but a bunch of feedback loops and delays interacting together. And I don't think I could have ever come to that conclusion and learned to think about things that way without taking this class. Also, this course, this course required a lot of writing, explaining in your models. Each part of the model has full documentation, and what you learn from doing this style of writing is how to describe things in such a specific way. How does this affect this? And learning how to explain your model in those kind of words where there's no alternate meanings that can be taken is a very good key to have. And really just a new way to solve real world problems. So it's, doing it with this mathematic modeling on a computer is really a great way to solve problems. And I would have never even thought of how to solve a problem such as a complicated business model without this. But with Stella, it was easy. So, this course and learning system dynamics has been a great thing. And it's actually helped me significantly in understanding a lot of concepts further in my engineering career too.